Hello, good day. This video we're going to look at the product rules some more, and this time the focus is going to be less on the understanding and more on the process, because it's the algebra that ends up giving most people the trouble here, not the actual derivative itself. Nonetheless, we need to start with a function, and our first job is to recognize that this function is in fact the product of two different functions. There's the square root of x, which I write in power form since I'm doing calculus, and then there's 3 minus x squared, which is a parabola. So I'm taking these square root function and a parabola, multiplying them together to create a whole new function, and I want to now study its rate of change. Recall that the power rule, or the product rule, is written in such a way that if you know two functions are multiplied together, then in order to take the derivative, you need to only multiply one function by the other function's derivative, then multiply the other function by the one function's derivative, and if you add them all together, you will have the rate of change function. Again, it seems complicated, but compared to first principles, it's a piece of cake. So, the derivative will be the first function times the derivative of the second function. What I want you to notice is I did not take the derivative of the second function, I only set it up. This is like using a square root sign or any other kind of math symbol. It just says this derivative of this function has yet to be taken. Same thing in the second half of the statement. We have the original function g of x times the derivative of f of x. Carrying on with the derivative process, the first thing I'm going to do is take the derivative of this function, which is itself a composite function. So I have to remember the chain rule within the product rule. So here, we multiply the 2, that's multiplying by the power, drop the power by 1, keep the inside the same, but the rate of change of the inside is going to affect the rate of change of the whole thing. So we multiply by the derivative of 3 minus x. Then we have the other half of the expression, so we have plus, and we'll have the 3x minus 2 and the derivative of x to the 1/2, that is, you multiply by the power, drop the power by 1. So notice the d dx went away because once I take the derivative of x to the 1/2, I don't have to take the derivative again, so I just leave it right there. Now I take the derivative of 3 minus x, which turned out to be negative 1. And then we bring down the plus sign. Everything else here stays unchanged. And now comes the mathematical cosmetics. So technically speaking, this is the derivative, but it's in such a messy state that it certainly used to be cleaned up. Now, the thing I'm about to show you is generalizable. It's something you'll always be able to use when you use the product rule, and that is look for common factors. Bottom line is there's an x to a power, and there's another x to a power. So I'm going to find the lowest power, and that's going to be the common factor for the x factors. There's also a 3 minus x here, and there's two factors of 3 minus x here, so that's going to be another common factor between these two expressions. I start with x to the 1/2. That's 1 over x to the, or that's, let me see. 1 over x to the 1/2 is the same as x to the negative 1/2. So essentially I'm going to factor the x to the negative 1/2 out, which if I do that, x to the 1/2 divided by x to the 1/2 is x to the 1, by x to the negative 1. We'll talk about that one some more. For those of you that have some Algebra 2 skills that need some revisiting, this might be one of those things, is working with exponents. But if you wanted to check my work, you can multiply x to the 1 by 1 over x to the 1/2. You subtract the exponents and you get back where you started. So, anyway, the negative 1 and the 2 are multiplied to give me negative 2, and the 3 minus x is carried down. 3 minus x squared, nothing happened, but I took out an x to the negative 1/2. That's what it is right here. If I were to redistribute, I'm going to multiply 1/2 times x to the negative 1/2. Now I'm going to look at the 3 minus x factor. I'm going to take that out, which leaves me with the negative 2 and an x. 3 minus x is taken out, which I still have 1 left over, so I leave the 3 minus x there, and then there's the 1/2. The rest of this should be algebra 1, or 2, I guess. So here, I distribute the 1/2. I'm going to collect like terms. So collect like terms over here. And the last thing I could do is recognize that both of these still have a common factor of 1/2. I could take the 1/2 out, giving us negative 5x plus 3. And, looking at my given form, it has 3 minus x, negative 5x plus 3, all over 2 square roots of 2. So I just have to multiply the numerators, and I get what I needed. Now, the extra bonus here was a thought question, and it said, well, where are the x's, or for what values of x will we have horizontal tangents? Well, this is a rate of change function, so I know horizontal tangents means 0 slope. So essentially, I'm asking the question, when does the derivative equal 0? Well, the thing about fractions is if the numerator of a fraction is 0, then the fraction is probably 0. So in order to make the numerator 0, we need to set x equal to 3, because 3 minus 3 is 0. Or we can make x equal to 3/5, which would give us 3 minus 3, which is 0. So when this is equal to 0, then I'm going to have 0 derivative, which is a horizontal tangent. So when x is 3 or when x is 3/5, we will have a tangent to the curve that will be horizontal. So that's stuff that we're going to see as we proceed further down the line. But for now, we're just going to see we have the ability to understand some further calculus. Thanks for watching. Have a good day.